Well, the two of them, the majority of the class didn't show up on Friday, so let's just go over what we had done on Friday, and today we will be mainly doing some applications of what we had done. So I think so you didn't listen to any of this magnetic field discussion, right? Did we? On the last lecture? On Monday? Oh, okay. So basically on Wednesday, these were what we had done. We had said that, okay, let's have a magnetic dipole moment. Let's assume that this magnetic induction is similar to the electric field created by the electric dipole. The torque expression, let's assume them to be also similar to the electric dipole case. And then we said that, okay, from these two information, we can actually measure the magnetic dipole moment and the magnetic induction. And then once you know you have a way of measuring this magnetic induction, then you can make experiments with it, and you can see how it depends how it is created. And we saw that if you have a current carrying wire, you can write the magnetic induction it creates by just considering the wire as made up of very small segments. Each segment will create a magnetic induction given by 1/c and that expression over there in the rectangle. Furthermore, the current, well, we didn't really do much about the current. Maybe today we might discuss a bit about the current and current in conductors. We will do more later on. The current and the charge density, they are related by this, what we call the continuity equation, which basically states that if you have a region of space, if the charge in this region is changing, that should be because of a current on the surface of that region. Either some charges are entering our region so that the charge density is increasing, or some charges are leaving the boundary of my region so that the charge density is decreasing. And the mathematical statement of this fact is what we call the continuity equation. And since we are dealing with statics for the time being, all the time derivatives should be zero, so that one property of the current should be that it should be divergenceless. The divergence of the current should be zero. So that is something we will be used to derive other properties of magnetic field. And in general, we said that, so this is the expression in the rectangle is the magnetic induction created by a single line of charge, single line of current carrying wire. Now, in general, you have any moving charge system will be creating a magnetic induction. And at least in magnetostatics, the magnetic induction can be written as an integral over the current density. Now, the current density, just like current in a wire is nothing but the charges that passes a given point per unit time, the current density is the amount of charges that passes a unit area per unit time. So it is like the current per area. And to measure this charge current, what you can do is just imagine, take a region of space where you have moving charges, consider an area perpendicular to the velocity of the charges, measure the current passing through this area, divide by the area, that gives you the magnitude of the current density. And the direction of current density is the same as the direction of the velocity of our particles. And then we also discussed the properties, what these expressions reduce for a point charge, and we just obtained the general expression that you would see, especially in high school books, in even some general physics books, that the magnetic induction created by a single moving charge is nothing but Q times V cross R over R cubed. This expression is not correct. So this is something you will see, this is something you see even in your book. But this expression is not correct. This is just an approximation. And the problem with this expression is that although the integral representation of this magnetic induction we had derived for magnetostatics, a single moving charge is not a magnetostatic system. The system is not static, it's dynamic. So we have to have all the machinery of the electrodynamics to evaluate the magnetic field of a moving charge. But of course, you can say that the charge is moving slowly. Now, when you say something, if you have a dimension full quantity like the velocity of this charge, and you claim that it is slow, you have to be comparing with some other velocity. And in magnetic problems, the common velocity, the characteristic velocity is just c. You see, we had seen this for the time being, this is just a constant and appearing in the expression of B. This is just this overall constant. We had shown that it should have the units of 1 over the speed. And so we call that speed C, so that constant turned out to be 1 over C. And that is kind of the defining speed in magnetostatic problems. So if you claim that something is slow, it should be slow compared to C. And numerically, that constant C turns out to be equal to the speed of light. Later on, we will see that it is actually the speed of light, but for the time being, it just seems to be a numerical coincidence. And if the charge is moving slowly, then this is the magnetic induction it creates. It will be just circles around the velocity of the particle. So if you have a particle moving towards the right, in that case, the magnetic induction will be towards you in the upper part and away into the screen in the lower part. And we had two more properties of this magnetic induction. One thing we had seen was the magnetic induction could be written as the curl of some other vector field, not written over here, but since it is the curl of some other vector field, its divergence is automatically 0, which basically tells us that there are no magnetic charges. It's like the electric charge. We have this electric charge which create electric point charges, which create electric fields, and electric field lines either leave from this point charge or terminate at this point charge, depending on whether it's positive or negative. But since the divergence of the magnetic induction is 0, there are no such point charges for the magnetic field, magnetic induction field. So the magnetic induction field lines cannot terminate at any point, or they cannot start at any point. They should either go to infinity, or they should make closed loops. There's no other alternative. Well, the curl of this magnetic induction turns out to be proportional to the current density at a given point. Or we can write this in an integral form. If we just consider any closed loop, integrate this magnetic induction over this loop, it will be equal to the total current running through this loop. Now, we had one application of this, the magnetic induction of an infinite wire. And one thing you have to pay attention to is the direction of the current. Well, the current is basically a number, but still it can be positive or negative. So depending on your area vector. So we say the current is the total charges passing through an area, but that area has a direction. So the charges can be passing in the direction of the area or in the opposite direction. So if the charges are passing in the direction of the area, then we say that there is positive current. If the positive charges are passing in the opposite direction, then we say that the current is negative. And in this line integral expression, you see the left-hand side is an integral over an area. The right-hand side is the left-hand side is an integral over a closed surface. The right-hand side is an integral over the area. The direction of the area should be consistent with the direction of this loop by the right-hand rule. If you just curl your fingers in the direction of the loop, your thumb should point in the direction of the area vector. Okay, then we had this other example of an infinite sheet moving with some velocity v. We had seen that the magnetic field is independent of the distance, it's uniform, etc. So here, for example, the magnetic field lines do not seem to be forming closed loops, but they go to infinity. They basically close the loop at infinity. And then we had this, we started studying the Lorentz force. This is the expression of the Lorentz force. So if you have put a charged object in a region which has an electric and magnetic field, well, if you have a charged object, in general, it will feel a force if there are electric and magnetic fields in the region. And this force will depend on the velocity of this charged object. And later on, this distinction will be important. What we actually call the electric field is the field that causes a force to act on a charged object, and this force is independent of the velocity. And there is a part that is linear in velocity, And that part is what we call the magnetic force. Now, this definition of electric and magnetic fields will be important later on. That's why I'm stressing it now. Okay, then we looked at the problem of two loops. Well, the issue here that we wanted to discuss is, did we write an example? Yes, here. Let's just assume we have two charges moving at 90 degrees with each other, and they are moving slowly, so that we can use our previous expression. Now, the problem was the forces that they exert on each other. Since they are moving, they will be creating a magnetic field, and this magnetic field will exert a force on the other charge. But these charges, since they are always perpendicular to the velocity, they will not be forming action-reaction pairs, which is Einstein's third law. Well, of course, it might be that the Einstein's third law is not correct, but the problem is Einstein's third law tells us that the linear momentum is conserved. So if Einstein's third law is not correct, then we have to give up the momentum conservation, which is not something we like. In particular, if you look at your classical mechanics courses, I don't know if you have already studied it, but the conservation of linear momentum is nothing but the symmetry of space under translations. So if you say that the linear momentum is not conserved, then you are practically saying that your space-time is not translational invariant, which is not nice, let's say, to say the least. But then, even in this approach, there is this problem that this magnetic field law we use is not a static. This problem is not a static problem. That's really the cause of this kind of discrepancy. You see, as the charges are moving, both the electric and magnetic field in space is also changing. Now, eventually, what we will say is that this electric and magnetic field themselves carry momentum. They have their own linear momentum. So that is not something we know. We know how to calculate yet. So then we try to look at the same problem, whether these action-reaction pairs are conserved, for two current-carrying wires. This is a static problem. So although the charges are moving, the charge density is not changing, the current is not changing. So the electric and magnetic fields in space and time, they are not changing. So even if the electric and magnetic fields, they carry some linear momentum, that linear momentum is constant, since they are not changing. So for this system, we should have action-reaction pairs. The forces that the first loop exerts on the second one and the force that the second loop exerts on the first one should form action-reaction pairs so that the momentum will be conserved. So we just start by the force law. The force acting on a current-carrying wire is if you put the wire in a magnetic field, then you divide it into small parts. Each one of these small parts will feel a force, and the force they will feel will be proportional to the current. It will be inversely proportional to this constant C, and its direction and magnitude will be given by this dl cross B. Now, we did all these tricks to evaluate those integrals, and eventually we could convert this force acting on the first loop due to the second loop to this form. So it is 1 over c squared. Well, the 1 over c squared is the magnetic induction produced by one of the loops is proportional to 1 over c. The force that the other one feels in this magnetic induction is also proportional to 1 over c. So we have that factor of 1 over c squared. And the magnetic induction will be proportional to the current. The force that the other loop will feel will be proportional to its current. So that's why we have this I1 times I2. And we have the two line integrals over each one of these loops of this delta 1, 2 hat over delta 1, 2 squared, where this delta 1, 2 is basically, so what we are doing is this dl1 integral is an integral over our first loop, We divide our first loop into very small bits, call each one of those bits by dl1, and then we have to evaluate the magnetic moment. We have to sum over the magnetic moments created by each one of the pieces in the second loop. And each one of these pieces, we call them their length dl2, is along the current. So these are dl1 and dl2 with the vectors we defined along these two paths. And delta 1, 2 is nothing but the vector connecting them. So this is our delta 1, 2. This is the delta 1, 2 vector. Well, we don't need to evaluate this integral. This already proves what we wanted.
Why would you add the minus?
Yeah, I didn't add the minus sign. It just came out of the calculation. So basically, in the calculation, what we did was, okay, we just first put the expressions for the magnetic induction and the force into our expression for the force, and we have that double cross product, and we had to evaluate that double cross product. Now, this double cross product we can expand in terms of as a linear combination of two of the vectors through this expression over here. Here we have that minus sign. And the first term just turns out to be 0. We are left with the second term. Now, if we were to calculate the force that the second loop feels due to the first loop, the only thing we need to do is just exchange 1 and 2. But if we exchange 1 and 2, that delta 1, 2 hat vector changes sign and nothing else changes. So the two forces that these loops feel, they are of equal magnitude, just pointing in opposite direction. So that is kind of, they satisfy the Newton's third law. And then finally we were looking at the work done by a magnetic force, and what we said was the magnetic force does not do any work. Whatever the circumstance is, magnetic force never does work. And then we had this example. Basically, we have a region of space which carries a uniform magnetic field into the screen. In this region, we put a current-carrying wire which carries some weight M. And if the current running, well, if due to the current in a magnetic field, this loop will feel a force, and if the current is equal to mgc over BL, in that case, the force acting on the wire will balance the weight of the mass, so hence the object will just stay in mid-air. But then if the current running through the wire is larger than this I0, this critical current, then the force acting on the wire will be larger. If the force is acting larger, the wire will be moving upward. Well, if the wire is moving upward, there is work done on the wire. Then the question is, what is doing this work? So we said that it's not the magnetic field cannot be doing any work. We calculated the force due to this magnetic field, and that force does work. So isn't the magnetic field doing any work here? Well, to understand what's going on, we started first with a simple example of a point charge in a uniform magnetic field. Here our claim was that, okay, there is some work done, but when we have this wire moving upward, it's the charges moving upward. So the charges are no longer, they don't have a horizontal velocity anymore. Their velocity has a small vertical component. So the magnetic force acting on these charges as they are moving along the wire is not vertical. It has also a horizontal component. Now, another observation we have is as these objects are moving in this magnetic field, they will be bending upward, the charges. So as they bend upward, they will be hitting the surface of our conductor. and then bounce back because they cannot leave the metal. So that means the metal itself will exert a force on these charges when they hit the surface of the metal. But that also means that these charges, when they hit the surface of the metal, is exerting a force on the metal. And this is actually what is creating this upward force. So what causes my charged objects to move? Well, the electric field in the conductor, which is created by the battery. So we connect the system to the battery, it accelerates the charges, it causes my charges to move in one direction, but as they move, they bend upward, and as they bend upward, they will hit the surface, exerting a force. And then they will bounce back. So it's actually the electric field that is doing work and transferring their kinetic energy to these charges, causing the charges to acquire a kinetic energy. And once they have that kinetic energy, they are hitting the magnetic field causes them to hit the surface without doing any work. It just changes the direction of the velocity. It doesn't change the speed. And when they hit the surface, they exert a force on the wire. Now, to study this problem a bit in more detail, what we did, we first looked at a charge moving in a uniform field. We said that it makes circular motion. It will make uniform circular motion because magnetic field doesn't do any work, and hence it cannot change the kinetic energy. It only changes the direction of motion. And then we found a relation between the charge, the mass, and the radius, etc. Now let me also, I didn't show it last week. Let me show you a picture.
And could we say that the work done is not because of the magnetic field, but because of the conductor?
Because of the electric field. Electric field is doing work.
Viewers, today we will be...
Okay, this is the discovery of the positron. That track you see over there is the positron. Is to detect part. This should be a bubble chamber. A bubble chamber is basically either an overheated liquid or undercooled gas. So that, I mean, for example, when you are told that water boils at 100 degrees, you can create water at 110 or 120 degrees if it is pure enough. But any disturbance in the water will just cause it to boil. So these particles, as they pass through these supercooled or superheated systems, they create this disturbance and they cause bubbles to form. And so by just taking pictures of those bubbles, you can determine whether there was a particle passing through the system, and you can determine its trajectory. Now this is one of such a picture. Now the problem with these pictures is that you don't really know which direction the particle is moving. So this is a system where you have a magnetic field. It should be into the screen. The magnetic field is into the screen, so this particle can be moving either upward or downward. To be able to tell which direction it moves, what they do is they just put this metal plate in the middle. In the middle, that dark region that you see is a metal plate. Now the advantage of the idea of putting that metal plate is if you have a charged object, as it's crossing this metal plate, it will lose some of its energy. So before it passes the plate, it will have a larger energy than after it passes the plate. Now let's see. For a given charged object, how does the radius change as the energy changes? A larger energy object. If the object has a larger energy, what happens to the radius? Does it get larger or smaller? Smaller or larger? He said smaller, you said larger. Well, you see, a larger energy object has a larger velocity. The left-hand side is a constant for a given object. The right-hand side should also be a constant. C is a constant, B is a constant in your system, so if V increases, R should also increase. So an object that has a larger energy should have a larger radius. So just look at this two segments. Does it have a larger radius above the plate or below the plate? So below the plate, it's almost a line. A line is a circle with an infinite radius. So below, it has a larger energy than above. So this already tells us that the object enters into our picture from below and it goes above, moves above. So we know the direction of the velocity. So what is the charge of this object? We know the direction of the magnetic field. We know the direction of the velocity. V cross B is already in that direction. That is the direction of acceleration. But the acceleration should be in the direction of the force, which is Q times V cross B. So Q has to be positive. So we already know that it is a positively charged object. And hence definitely it's not an electron. You already know by preparing this setup, you know the magnetic field. You know the C. You can measure the radius by just looking at these trajectories. So basically you know kind of everything on the right-hand side, if you know the energy. You know the velocity, you know the C, you know R, you know B, so you can determine the Q over M ratio. And in that experiment, at least, it turned out that it is a positively charged object with the Q over M ratio that is exactly equal to the Q over M ratio of the electron with the opposite sign. So that is the first time we had observed a positron, the positively charged electron, the antiparticle of an electron. Now, of course, this is a single charged object in a uniform magnetic induction field, and assuming the velocity is perpendicular to that magnetic induction. Well, in general, if it is not perpendicular, it will just form a helix, because there cannot be any force in the direction parallel to the magnetic field, because V cross B is always perpendicular to B. So the component of the velocity in the direction of B never changes. And then eventually we said that, okay, the Earth being a big magnet, where is the magnetic north pole of Earth?
South.
It's on the geographic south. So this is the north pole, this is the south pole. These lines are not correct, this is not correct. Yes. So we have these solar winds. They are just charged particles coming from the sun. So when they arrive in this region, they will start rotating around these magnetic induction lines. And furthermore, since they have a component along the direction of these magnetic induction lines, they will also move, they will go along helices. And these helices, they will take these charged objects into the magnetic north and the south pole, which are more or less the geographic north and the south pole of Earth. And we have these charged objects. They are usually energetic, so they will just move to the poles and they will collide with the atmosphere over there with the oxygen and nitrogen, exciting them. And when they are de-excited, they will emit light. These are what we call the northern lights. And of course, in this region, there is lots of radiation. So that is something also you have to take into account when you are planning constructing satellites or sending space shuttles in space. So this is a zone high in radiation. So that was what we had done last week. Any questions?
curl of B is 4 pi over Cj. I think we could have used in derivation we have alternated between R and R prime. Couldn't we have continued with R instead of R prime?
Now let me open that one. Hmm?
I did a lot. Okay.
This is the curl of B. Okay, then we had the first one. How do you plan to show that the second one is 0?
I don't know, used the notation.
Mm-hmm.
It worked. It gave this 0 for any, even for the non-static case. Just do this.
Well, let's see. Let's redo it. Let's repeat it. So we already know that B should be given by this integral. D cubed R prime, J of R prime, cross R minus R prime over R minus R prime cube. And the idea was to calculate the curl of B. Let's say the I component of curl of B, which is 1 over C epsilon I j k del over del xj bk, which is 1 over C epsilon I j k del over del xj. Well, bk is, I'm sorry, there's no, it's 1 over C. Now here we have 1 over C, and bk is d cubed R prime epsilon k l m jl prime. Jl prime is jl at the point R prime. This is the notation I will be using. And R xm minus xm prime divided by R minus R prime cube.
Yx.
The components of R, I just call them xi, jk, xi, xj, xk. Well, let's take the derivatives. This is 1 over C epsilon I j k epsilon k l m d cubed R prime jl prime del over del xj xm minus xm prime over R minus R prime cube. Now your proposed, let's just open up this product of two derivatives. That will be Kronecker delta IL Km, Kronecker delta I, no not K, Jm, Im, Jl, d cubed R prime, Jl prime. Now your proposal here to take this derivative, straightforward. Okay, let's take that derivative. Well, let me just move it down. So the derivative of xm minus xm prime is Kronecker delta Jm divided by R minus R prime cube, and plus xm minus xm prime minus 3 over R minus R prime to the fourth, and then I would have xj minus xj prime divided by R minus R prime.
So you have not exactly what I had. It doesn't continue from what we had done on Wednesday. What we did on Wednesday is that we replaced.
Yeah, that's, I mean, what?
This function by the gradient of it. By the gradient of another function. The function of 1 over the distance squared.
Okay, let's go it that way. Let me remove this one, so this will be del over del xj, del over del xm, 1 over r minus r prime. And there's a minus sign. This one is xm. I can convert it to xm prime if you like.
So now, can't we prove that this vanishes directly without converting it to its prime?
I don't know.
If you take the product with j.
How?
Take this product with j.
Well, you see, this one, by the way, should not vanish. That is where we get the Dirac delta. And that's what gives us 4 pi over Cj at the point r. You see, when j is equal to m, that's just Laplacian acting on 1 over r minus r prime, and that would give me a Dirac delta function. The first one should be, the first one will cancel some of the terms from the second one. The second one is not just a pure Dirac delta. There are additional terms coming from the second one.
Can we continue with it?
Sure. Now let me first study that derivative. So let's find an expression for that derivative. So I will be basically looking at this derivative. 1 over r. I don't want to write r minus r prime, etc. Then at the end, eventually, I would just replace r with r minus r prime. Now, if you just take the derivative in a straightforward manner, this will just give me del over del xj. Derivative with respect to xm will just give me minus xm over r squared, which is minus Kronecker delta jm and minus xm times minus 2 over r cubed xj over r. Here I have an r squared. So this will be, do you agree? Now what I did was, should I do it more explicitly? Okay, let me do it step by step. From now on, I will be using index notation more often. So this is derivative with respect to r of 1 over r multiplied with the derivative of r with respect to x mu, xm. Which is del over del xj times minus 1 over r squared del over del xm. Well, r is nothing but xl times xl squared under the square root. So this is equal to del over del xj minus 1 over r squared. And remember, this derivative with respect to xj is the derivative of everything. 1 over r squared. Well, here the derivative is 1 over 2 times xl squared to the power minus 1/2. I'm just again using the chain rule once more. And then the derivative of xl squared with respect to xm, which is del over del xj minus 1 over r squared, 1 over 2, 1 over r, xl squared, and remember, I am summing over l's. So that xl squared is nothing but r squared.
So minus 1 over 2 power, it's for the sum.
Yes, yes, sure. It's the minus. First I am summing over L, then taking the minus 1 over second power. Derivative of xl squared is twice xl. Derivative of xl with respect to xm. 2's I will cancel. This is del over del xj minus 1 over r cubed times xl. That derivative, the derivative of xl with respect to xm is, well, components are independent of each other. So if L and M are different, it is just 0. If L and M are the same, it's just 1. So it's Kronecker delta Lm So what we obtain is del over del xj, del over del xm of 1 over r. This is equal to del over del xj minus 1 over r cubed. I'm summing over L, but due to that Kronecker delta, only the L is equal to m term survives, and that gives me xm. Now I will be taking the derivative with respect to xj. So this will be minus derivative of xm with respect to xj times 1 over r cubed minus xm times derivative with respect to xj of 1 over r cubed. I'm just using the derivative for products. This will be equal to minus the first one. Again, if m and j are the same, it's 1. If they are different, it is 0. Kronecker delta mj, 1 over r cubed minus xm. This is the derivative with respect to r of 1 over r cubed, and the derivative of r with respect to xj. Minus the Kronecker delta mj, 1 over r cubed, minus xm. This derivative is minus 3 over r to the 4. I will not repeat the derivative of r with respect to xj. It will just give me xj over r. And then I have the result is, let's see, this is r. This is 3xm xj minus Kronecker delta mj r squared divided by r to the 5. Of course, this is true if r is different than 0. If r is 0, I cannot just take the derivatives. Now let's see. Let's just multiply both sides by Kronecker delta mj. The left-hand side just gives me the Laplacian of 1 over r. The right-hand side gives me 3xm squared minus Kronecker delta mm r squared over r to the 5. What's Kronecker delta mm? It is 3. Remember, I'm summing over m. It is repeated. So this is 3. Well, xm squared is just r squared. So this is just 0. This is, of course, assuming if r is different than 0. So basically, we are missing this Dirac delta. Now, let's look at this one. Well, to see whether there is a Dirac delta or not, we just need to consider the integrals over a region which contains the origin. Now let's look at the M is different than J case. And let's integrate the left-hand side over a sphere. Well, the sphere is symmetric in the xj coordinate. Right? 1 over r is symmetrical with respect to xj coordinate. But the derivative of 1 over r with respect to xj is anti-symmetric with respect to the xj coordinate. So if you have an even function, its derivative is odd. If you have an odd function, its derivative is always even. Just think of, for example, sine. Sine is an even function. If you take the derivative, it's cosine. It's an odd it's an even function. Sine is an odd function. If you have a cosine, if you take the derivative is the cosine is an even function. The derivative is a sine, which is an odd function. So 1 over r is an even function in xj coordinate, so its derivative is an odd function in xj coordinate. If you integrate an odd function over an even interval, a sphere is symmetric in the xj coordinate, the integral is 0. So basically, if you integrate over xj only. Well, since we are taking a sphere, I mean, here of course I have the other coordinates, d squared x. The other coordinates are outside. So in this integral, I'm setting xj from minus xj0 to plus xj0. The interval of xj is even. The derivative is odd, so this is automatically 0. But of course, I'm assuming that I can take the xm derivative out of the xj integral. Xm integral is out. Well, this basically tells me that this is equal to 0 if j is not equal to m. So if j is different than m, there is no Dirac delta. And I'm only considering a very, very small region around the origin, so I kind of ignore the first part. I'm just looking at whether there's a Dirac delta or not. But there should be a Dirac delta if j is equal to m. So that tells me that this del over del xj, del over del xm of 1 over r, this should be equal to 3xm xj minus Kronecker delta mjr squared over r to the 5th plus, if j is equal to m, I have a 3-dimensional Dirac delta. Let's say I don't know the coefficient yet. Now I need to determine what this coefficient a is. And to determine the coefficient a, what I do is I just multiply both sides. By Kronecker delta jm. The left-hand side gives me the Laplacian of 1 over r. The right-hand side, well, the first term gives me 0. We had already seen that. The second term, the term containing the Dirac delta, gives me 3a Dirac delta 3 of r. But I already know that the left-hand side is 4 pi Dirac delta of r. So this tells me that a should be equal to 4 pi over 3. So now what did we show? This derivative is equal to this one for all points R. This is something you can always use. Now let's go back to our expression. Remember, we were trying to calculate the curl of the magnetic field. And we had seen that the curl of B, the I component, is equal to this one, which is equal to 1 over C I L Kronecker delta J M I M J L times D cubed R prime J L prime Kronecker delta J M over R minus R prime cube minus, well, this derivative is 3xjxm minus Kronecker delta Jm R squared. Okay, now I have to also replace x minus R prime J, R minus R prime M, minus Kronecker delta Jm, R minus R prime squared, divided by R minus R prime cube. This is the term without the Dirac deltas. And then I have the plus or minus plus 4 pi over 3 Dirac delta 3 of R minus R prime. Minus, yes. And I also have Kronecker delta Jm. Now let's open the parentheses. You see, Kronecker delta IL, Kronecker delta Jm minus Kronecker delta Im, Kronecker delta Jl, multiplied with Kronecker delta Jm would be just twice Kronecker delta IL. Because this term, Kronecker delta Jm multiplied with Kronecker delta Jm will give me 3. From here I will get 3 Kronecker delta IL. From this one, Kronecker delta Jm multiplied with Kronecker delta Jl will just give me Kronecker delta Lm. And multiplied with this one, it will give me a Kronecker delta IL, just one of them. So curl of B prime, Bi, this is equal to 1 over C twice Kronecker delta IL. I'm just first writing the Kronecker delta Jm terms. Integral of J prime L D cubed R prime over R minus R prime cube and now this is the this term we wrote. Then I have this minus 4 over 3 minus 4 pi over 3 and the integral of Dirac delta just gives me JL. There's no integral on that second term. And then I need to consider this product.
It's over 3 over 5.
Hmm?
Is it over the power of 3 or the power of
4 pi over 3. Which one? Over 5. Yes, yes, yes. Let me first calculate that product. Let me take this factor. Multiply this with 3xm xj minus Kronecker delta mj x r squared. Then I will just substitute it back. This will be equal to Kronecker delta IL and r squared, Kronecker delta Jm multiplied with xm xj just gives me r squared. This is the product of the first term. The first term and this last term just gives me, well, basically this Kronecker delta Jm multiplied with this one already gives me 0. That's something we had already seen. So this term gives me 0. And the other term just tells me that instead of m, I should replace it with I, and instead of j, I should put it L. So let's write it again. I have another minus over here, so that makes a plus 1 over c. D cubed r prime, and 3 jl prime, 3 x r minus r prime L I r minus r prime L minus Kronecker delta I L r minus r prime squared divided by r minus r prime to the power 5. This is the I component of the curl of B. So curl of B, the I component. Let's see. We have minus 8 pi over 3 C Ji. This is this term. And plus 1 over c. All the others have some integrals, d cubed r prime, jl prime. Do I have some more cancellations here? Let's see, this Kronecker delta IL, I have a Kronecker delta IL over there. This term and this integral, they have the same form, same coefficient, etc. So the overall coefficient of the term in integral in the first line is 2. In this one, I have a minus 1. So there's just 1 left. So basically, that sign between these two terms becomes 1. Plus the Kronecker delta IL r minus r prime squared divided by r minus r prime to the 5th. Now, we have to simplify that integral, and remember, we should still get some j's from there, some Dirac deltas from that last term. Because if you remember, our final expression was curl of B should be equal to 4 pi over Cj. This was the final result we had. So we should get many J's, many Dirac deltas from the second integral.
Should get where is the derivative that will be derivative?
Hmm?
Where is the derivative that will be the Dirac delta?
I don't know.
I guess we must have made a mistake on the
Well, either we made some, you see, one thing we could have done, we can still do. Let's look at this one, JL prime. Or let me rather look at this one, XL J, and take its divergence. This will be equal to del over del xi, xlji. This will be equal to del xl over del xi, ji, plus del over del xi, ji multiplied with xl. This will be equal to Kronecker delta I L Ji plus the divergence of J XL, which will be equal to JL plus 0. So JL, the L component of J, I can write it as the divergence of XL times J. I should put it over here. Now I have the derivative. I should do an integration by part. Then when I do an integration by part, that derivative will move here. That will give me more Dirac deltas. I'm sure you are happy with the previous derivation now.
If we do that, we get what derivative will be with respect to prime.
Well, you see, this derivative over here, you can either write it in this form or JL prime. Yeah, I mean, since we have the JL prime, we have to write it with respect to the XL prime. So then we can, if you do integration by part, that derivative with prime coordinates will go to the other term, which contains that 1 over r minus r prime to some power. And that expression is already kind of a derivative. Derivatives of 1 over r minus r prime. So you take another derivative, that brings you a second derivative, which contains your Dirac deltas. So that will give us more j's factors. And eventually we should get 4 pi over 3 times j. A nice exercise for your next homework. Anyway, let's do some simpler cases. So remember what we were looking at, my claim was that the work done was due to the electric field. Let's first give some more justification to this claim. Now, on one hand, we said that, okay, so we have this region of the magnetic field. I have this wire moving upward. Let's say at a given instant it's moving with a velocity u. So the charges in my wire basically have a velocity v, which creates my current, and a velocity, an upward component of the velocity. So this will be their total velocity, and this will be the total force the force that they will be feeling, which has a component perpendicular to v, and another component parallel to v. And let's call this angle theta. This angle will also be theta. F, remember the magnitude of F will be just, if you have a single charge, it will be Q times V prime times B. So the magnitude of the perpendicular component will be Q times V prime times B times cosine theta, which will be Q times V prime times B times, well, cosine theta is nothing but V over V prime. So V prime will cancel, this will be equal to QVB. Well, the vertical component is just as if my particle is moving horizontally. And the parallel component, the magnitude of the parallel component will be QV prime B times sine theta, QV prime B times, well, if you look at the triangle of the velocities, sine theta is nothing but U over V prime. V primes cancel, so it is QU times B. This is the parallel component. This is the force acting on a single charge. So let's call the lambda be the number density of current carriers. So I have some current carrying particles. They are moving with the velocity v prime, and I have lambda of them per unit length. And let's say this length over here is A. So lambda times A is the total number of current carriers in my wire. The total perpendicular force will be just lambda times A times F perpendicular, which will be lambda times A times Q times V times B. Well, you see, lambda times A is the total number of charges that I have. Lambda times A times, no, sorry. Let me move V here. Lambda times Q, lambda is the total number of particles. Lambda times Q is the total charges that are in motion. If I multiply the number of charges by their velocity, I get the current. So lambda times Q times V is nothing but my current. So this is I times A times B. This is the force that we already have. Now the parallel component of the total force is, again, lambda A is the total number of charge carriers I have, then F parallel, which will be lambda times Q times UAB. Now let's calculate. Okay, this is the horizontal component of the magnetic force. And if my charges are to move along the wire, the battery should be pushing them with this force. So let's calculate the work done by battery per unit time, or the work done by battery in a time dt. It should be exerting this force F parallel. In this time, the charges will move a distance v times dt. So this F parallel is the force that my batteries should be exerting on my charges. And v times dt is their displacement. This is lambda q times v times u times dt AB. This is I. This is I times A times B times U times dt. Well, I times A times B is nothing but the vertical force. But U times dt is nothing but the vertical displacement of my wire. So the work done by my battery is exactly equal to the work done by this force in the vertical as the wire is moving vertically upward. So we had seen it as the magnetic force, but it's actually the work of battery. The magnetic field kind of rotates its direction. And the mechanism for this to work is basically, as I said, the magnetic field rotates, the electric field accelerates the particles, and the magnetic field just rotates their velocity so that they hit the wire, and once they hit the wire, they will bounce back, exerting a force on the wire. But it's not the magnetic field that is doing the work. Let's do another example. This is also something we can solve explicitly. Let's say this is the z-axis, this is the x-axis, this is the y-axis. We will have a magnetic field, magnetic induction in the x direction. And also I will assume that we have an electric field in the z direction. So let's say this is the x-axis, this is the y-axis, this is the z-axis. Electric field is in that direction. You put a charge at the origin, and you wait for a long time. Where would you expect the particle to be after a long time? Somewhere over there. Electric field is in this direction. Do you expect the particle to be somewhere over there, somewhere over there, somewhere over there? What do you expect where do you expect the particle to be?
Above the x-y
Hmm?
Above the x-y
Well, above the xy plane is a large region. This is the magnetic field. You see, this is B. This is E. You put your particle over here, at rest, let's say, initially. And you wait a long time. Of course, its position will be something complicated that we will study, but where do you expect? Do you expect it to be along the z-axis, along the x-axis, along the magnetic field, along the electric field, somewhere in between, in that direction, somewhere over there? Your naive expectation. And the z-axis.
oscillating towards y-axis.
So it's not moving anywhere. Oh, that's also another option. You can say that it will not go anywhere. It will just stay around the origin, somewhere around the origin.
It will move in the y-axis, like the net.
In the y-axis. Okay, so 3 axes, 3 choices. One of you, at least one of you is right. Let's calculate it. Now the force is Q times V cross B, which will be Q times V will have the x component, y component, the z component. B has only the x component. Initially it's a 0. This is an arbitrary time. I will be trying to find the time evolution of the velocity and the position of the particle. Initially, the force I can calculate it, but I don't really care about that for at the time being. At an arbitrary time, it will have some velocity, and its velocity can have, in principle, x, y, and z components. And then at that time, this will be the force it will feel. Let's multiply it out. It's Q times B times Vx, x hat cross x hat is 0, plus Vy, y hat cross x hat minus z hat, plus Vz, z hat cross x hat, y hat. This is minus QB Vy in the z direction plus QB Vz in the y direction. There is no force, oh, sorry, this is Vz. But the force should be equal to mass times the acceleration. So mass times the acceleration in the x direction is 0. Mass times the acceleration in the y direction is qb/vz. Mass times the acceleration in the z direction is minus qb/vy. And I have an electric field in the z direction, so plus qe. That last term is due to the electric field. Do you agree? Let's write it as derivatives of the components. So, well, there is no acceleration in the x. Initially, we said if we assume that it is at rest, the initial velocity is 0 in the x direction. So there is no acceleration in the x direction, so the velocity in the x direction will always stay 0. If the velocity is 0, it will always stay at x is equal to 0 point. It won't be moving in the x direction. Now let's look at the y and the z. Mass times y double dot, this each dot is a time derivative, should be equal to q times p times z dot, and m times z double dot should be equal to minus q times p times y dot plus q times e. So we have two coupled system of second order differential equations. Now to solve them, let's just take the time derivative of the second equation. If I take this time derivative of the second equation, I get mz triple dot. This should be equal to minus qby double dot. Q times e is just a constant, so its time derivative is 0. But from the first equation, I know that this is equal, y double dot is qb over m times z dot. Or d squared by dt squared z dot. This is equal to minus qb over m squared z dot. So z coordinate is just doing some harmonic motion. So z dot, it should be equal to a times cosine, well, a omega times cosine omega t plus delta, where omega is, I define it to be qb over m. So if this is my z dot, then z of t will be a sine omega t plus delta plus some constant b. Now let me insert my initial conditions. I know that z at t equal to 0, or z dot at t is equal to 0 is equal to 0. Let me just make one more change. Let me just, instead of the cosine, use a sine over here with a minus sign, so that this z is a cosine. Z dot at t equal to 0 is 0, so this basically tells me that delta should be equal to 0. And then z at t equal to 0 should be 0. Well, this tells me that a times, well, delta is 0, a times cosine 0 plus b should be equal to 0, or b is equal to minus a. So we know that z of t should be equal to a times cosine omega t minus 1. I still don't know what a is. There's not enough information to determine a yet. Now let's look at the y expression. You see, this is the equation for y. Or we can look at this equation. It's already integrated once. So this tells me that m times, well, z dot is already over here. I just need to take its derivative once more. So it is minus a omega squared cosine omega t. Remember, delta is 0. This is z double dot. This should be equal.
Why is that a zero?
Boundary condition. Initial velocity should be 0. So we just release it from rest. This should be equal to minus QB y dot plus Q times E. So let's just simplify it a bit. We have y dot is equal to 1 over Q times B, Q times E, plus M times A. Omega squared is QB over M squared, two of them, times cosine omega t. This is y dot. Well, let's open up the parentheses. This is E over B plus A. One of the QB over M's is cancelled. A omega cosine omega t. This is y dot. Or y of t should be equal to E over B times t plus A times sine omega t plus some constant c. Now I will impose my boundary conditions. On one hand, I know that y dot at t is equal to 0 is equal to 0. So this tells me that E over B plus A omega should be equal to 0. Or A should be equal to E over B omega. Now I know A. And then I know that y at t equal to 0, this should be 0. Minus, yes. Y at t equal to 0 is E over B. No, there's no E over B. A is just C. So this tells me that C is equal to 0. So y of t should be equal to E over B times t minus E over B omega times sine omega t. Or E over B omega t minus sine omega t. This is our y of t. And we also have the z of t. Now, what kind of a motion is this? If you look at the z-coordinate, the z-coordinate just changes between, well, A we had already determined it to be minus E over B omega.
Is this cos-cycloids?
Yes, this is E over B omega times 1 minus cosine omega t. Is the z-coordinate, the coordinate in the direction of the electric field, just changes between 0 and twice E over B omega. So it doesn't move away in the z-coordinate. The maximum value of the z-coordinate is fixed. But if you look at the y-coordinate, there is this modulation of sign, but it increases linearly with time. So if you just take its average over some interval, its average just moves linearly. Now we can do a bit more than this. Let's look at this one. Y of t minus et over b squared plus z of t squared. This is equal to, z of t minus e over b omega squared. This is equal to e over b omega. squared. You see the left-hand side in the left combination, when you write that down, you get E over B omega squared multiplied by sine squared from the y term, the cosine squared from the z term. So their square just gives us 1. Well, this would be an equation for a given time t. This is the equation for a circle. So basically, the motion is exactly the same as you take a wheel, choose a point on the edge of the wheel, and roll the wheel. That point that you have chosen follows this trajectory. And the shape will be this one. This is y, this is z. Yeah, due to our boundary condition, the bottom edge is a sharp point. If you had, in general, for a different boundary condition, it will look like this one. So this will be the trajectory of our particle. So one thing is, I mean, although the electric field is in the z direction, on the average, the particle is moving perpendicular to the electric field due to the presence of the magnetic field. So this is actually what's going on also in the wire. So you have this wire, you apply an electric field in this direction, but on the average, the charge will be moving upward, hitting the surface. But the metal will not let the charge to go out of this wire. It will exert a backward force. I mean, the metals are just like a particle in a box. You can think of them as particle in a box. Inside the metal, they are free to move, but on the boundary, there are forces keeping the charges inside the metal. So when these charges hit the boundary, these forces due to the metallic properties will push them back inside. But that means the charges will exert a force on the metal, and hence it will push the metal. And you see, furthermore, the center is basically moving at constant velocity. Is the velocity of the center of this circle is moving is E over B. By the way, I forgot a C somewhere at the start. Yeah. There's a C. Let's say I just chose C to be 1 in this problem. So the velocity is unitless. E had the same unit as B. So E over B is unitless. That is the velocity of the center. It's moving with constant velocity. It's not accelerating. On the average. Of course, the charge is constantly making this one. It almost always has an acceleration. But on the average, the acceleration just cancels. There's no average acceleration. It moves perpendicular to the electric field with constant velocity. And the speed depends on the ratio of the electric field to the magnetic field. Any questions?